right, so it's 4:01 already. It's time to get started with this class. So are there any questions from last week? Because last week we talked about a few properties of relations already. We talked about being reflexive and being symmetric, and I think we touched on transitive as well. We just started. Okay. So are there any questions regarding those specific properties? I don't have a mic with the amplifier today, so I can't use that one. It's out of battery. For whatever reason, they wanted to keep using alkaline batteries instead of rechargeable. So mine is using rechargeable. It's good for about a week. One set of battery is good for about a week or so. So every week I just take this back because I have another set at home that's already charged. So I just get the charged one, pop it in, get these back to the charger, and that's how I do it. So I don't understand why we are not using rechargeable batteries. Anyway, are there any questions about these two properties of relations? Okay, so yep, go ahead.
Never say that reflective can be symmetric.
Um,
Is it a special case?
it's not like that because reflexive requires that every element in a set relating to itself, but it can also have any other additional relationships between any elements. So it's not, if something is just reflexive and not anything else, then it is also at the same time symmetric. But an empty relation is also symmetric to begin with. So that's why I wouldn't relate those two because they are really quite different. Yep.
So kind of like what we just said,
Uh huh.
to make sure.
Yeah.
Like when you have something that's reflexive, it just means that like if you have A, B, C and stuff, you have to have A, B, B, and C, C.
Mhm.
But you could also have like A, B, A, C, B, all these
You
other
can
ones,
have.
as long as you have the original like A.
Yep. Exactly. So in your example, if your set X has A, B, and C as elements, a relation that is symmetric must contain AA, BB, CC, but it can contain any other two tuples, as long as the relation remains as a subset of the Cartesian product of X and X. So is that okay, or are there any questions about that particular description of what makes a relation reflexive? No questions about that part? Okay. All right, so when you look at reflexive, it doesn't really depend on implication, which makes it kind of easier to understand because there's no implication. Implication is sometimes making things a little bit harder to understand because, like in the case of symmetry, okay, symmetric, in order for a relation to be symmetric, it has not implication, but if and only if, which is a bidirectional implication. So in this case, if EF is missing, FE has to be missing as well. If EF is in R, then FE has to be in R. So that's why an empty relation where there's nothing in it is automatically symmetric because both are guaranteed to be false. No matter what E or F you choose from X, EF has to be missing from R, FE is also missing from R, which is fine because false, if and only if false, is true. Is that okay? So I think the confusion is when we use the word or phrase if and only if, most people think of it as an operation, like an action, but it's no more than and or it's just a logical operator, okay, which has its own result. So look at if and only if, as just an operator with its own result. False, if and only if false, gives you true. Okay. So are there any questions about symmetry or what makes a relation symmetric? So that part is good. All right. We talked about transitive as well. So transitive requires three elements and two relations. Okay. And I think last time, I specifically said that F is what I would call a bridge element, right? And I commented on how that is not traditional because that term is not used by textbook that I know of. But that's what it serves. Okay, when you look at F, the element that we chose from X, that we call F here, F is kind of like a bridge element because it's the second one in EF and it's the first one in FG. So it's kind of like bridging between E and G. Okay, so if the bridging action is actually true, in other words, if E relates to F and F relates to G and E relates to G in the relation, and if you can say that this is true for any way of choosing these three elements in X, then the relation is called transitive. Is that okay? Well, this also, yeah, go ahead. Is it possible for it to be transitive and symmetric at the same time? Yes. The empty relation is like that. An empty relation is automatically transitive because pick any three elements. They can be the same, they can be different, doesn't matter, okay? So pick any E, F, and G in X. Is EF in R? No, because R is empty. Is FG in R? No, it is empty. Is EG in R? No, it is empty. So we have false implies false, which is true. So an empty relation is automatically transitive and symmetric at the same time. So is that answering your question? What about something that is just reflexive and no more? It's barely reflexive. Well, it's automatically transitive, right? Because the only way to make the conjunction true is to have E, F, and G all being the same element. Well, if E, F, and G are all the same element, EG is a relation in a relationship if it is just barely reflexive. Okay? So is that good so far? Transitive? Okay. So now we move on to anti-symmetric. Anti-symmetric is a little bit awkward because it only needs two elements. So pick any two elements in X, okay? For every way to pick two elements in X, we need this condition to be true. What is it? It says EF in R and FE in R implies E and F are the same. So what does that mean? It's called anti-symmetric. So in normal comparison, can someone name a relation like that? In normal comparison, like less than, greater than, not equal to, that sort of thing, can someone name a relation in comparison such that if E is blah blah F and F is blah blah E, it implies that E and F are exactly the same thing? Equality? So equality is one, but that's somewhat trivial because uh, if E equals to F and F equals to E, then E equals to F. Okay. Yep.
Is it like being between two digits?
No. How about yeah?
Less than or
L- yep. Exactly. So less than or equal to in comparison and greater than or equal to also meet this requirement, and it's non-trivial because if x is less than or equal to y, and y is less than or equal to x, that implies x and y are the same. The same goes for greater than or equal to. It's just the flip side of it. Very good. So that's anti-symmetric, which is kind of like an odd one, because why do we need that? Yep. Um, transitive. Oh, okay. No, it's supposed to say anti-symmetric. Let's fix that. So let's do that. This one is 0312, I think. Okay, right here. Anti-symmetric is the word. And then we'll publish it again. There we go. And now it's fixed, I think. Yep, so anti-symmetric. There we go. Not exactly what you see is what you get, but I would say close enough. All right. So next thing we want to do is to look at what is partial ordering. All of these relations, why do we even care about all of these different properties of relations? It has to do with ordering. Well, but before we talk about ordering, we have to talk about partial ordering. So partial ordering is defined like this, okay, the first part of the section. A set X is said to be partially ordered by relation R if and only if the following are all true, okay? So it's implicit that, well, that's the word and, so that means they all have to be true at the same time in order for R to be called a partial ordering relation. R has to be reflexive over X, okay? We know what reflexive is. R is anti-symmetric, and R has to be transitive, okay? So getting back to an earlier example, less than or equal to, and in integers is partial ordering. Does that make sense? Okay, so let's check that, okay? So is less than or equal to reflexive over integers? In other words, if I ask you, of all integers that you can represent in any programming language, is a particular integer value less than or equal to itself? Check, okay? Is it anti-symmetric? In other words, if I say, okay, I got integer x, I got integer y, and if I tell you x is less than or equal to y and y is less than or equal to x, does that imply x and y have to be the same value? Yes. Is it transitive? In other words, if I pick any three integers, okay, does x being less than or equal to y and y is less than or equal to z implies that x is less than or equal to z? Yes. So it meets all of these requirements, so less than or equal to is clearly partial ordering, okay? But there are things that are less obvious that are partially ordered. So I'll go through this example down here, okay? If you haven't read it, that's why none of you guys are smiling, because very few of you have actually read this part. This is based on a beer commercial. Okay, do you guys remember that beer commercial? No? Smooth versus rich? Some of you do. Most of you do not seem to remember that commercial. I don't even drink beer, but I thought that commercial was kind of interesting from the logic perspective, and that's why I remember that one. So maybe it's good to show you that commercial first. Okay, beer commercial, smooth versus, what was it? Rich. Okay, I think it's an Australian beer. And here's the commercial. And we'll turn on closed captioning because the voice is not playing too well here. Okay, there we go. Rich. But not smooth. Okay. Next guy. Smooth. But not rich. He's doing at Best Buy, by the way, or something like that. So okay, so now we understand. In certain situations, people evaluate a potential mate, based on smoothness and richness. Okay, all right. I got to turn this off because otherwise I'll keep watching. It's not your problem; it's my problem. Okay, so what I'm going to do here is, I'll define a relation called is more desirable than. Okay. So we know that smooth and rich is more desirable than smooth but not rich. Smooth and rich is more desirable than not smooth but rich, and so on. I mean, it makes common sense based on the commercial. Okay. So obviously, more desirable does not meet the requirement of partially ordered relation because it's not reflexive. Okay. So if it's not reflexive, why is it not reflexive? It's not reflexive because smooth and rich is not more desirable than smooth and rich. Okay? Do you guys see how it is not reflexive? So we are not interested in that one. So we're going to change it. And we'll change it to is at least as desirable as, which is a long phrase. So I abbreviate that to alada. At least as desirable as alada. So you can now use that term to refer to people. You can say tag is alada, a rotten tomato. I'm pretty sure that's true from the eyes of fruit flies. Very few of you have compost bins, obviously. Because if you have your own compost bin, you will understand flies really like rotten tomatoes. So I'm going to petition ratemyprofessors.com to start to have rotten tomatoes in addition to hot chili peppers. You might like this professor if you were a fruit fly. Okay, so, but let's check this out, okay? We got 8 of these things, okay? Well, not 8. We got, let's see, we have a total of 16 relations, but we'll just kind of summarize to these because between rich, smooth, and rich, there's smooth and rich but not rich but not smooth, and then not smooth and not rich. And then we have to draw relations between any two possible pairs, and that's why there's a huge number of these. Smooth and rich is at least as desirable as smooth and rich. That works because they are exactly the same thing, right? So, and then the next one is smooth and rich is at least as desirable as smooth but not rich. Okay, you're missing one item. Smooth and rich is at least as desirable as not smooth but rich. Okay. And smooth and rich is at least as desirable as not smooth and not rich. Okay, so the first 4 items seems to make sense, right? Next few items. Smooth and not rich is at least as desirable as smooth and not rich because it's the same thing. Okay, we have quote unquote the equality. But we can also say smooth and not rich is at least as desirable as not smooth and not rich. Right? Having one attribute is better than having none of the attributes, and so on. And the last one is not rich and not smooth and not rich is alada, not smooth and not rich because it's the same thing. Is that okay? But I said 16 items, and how come there are only like less than 16 items here? Because the missing ones are basically not. Okay? In other words, not smooth and not rich is not at least as desirable as basically any of the other ones besides itself. Okay, but those are not listed here because I'm only listing the ones that are confirmed. So these ones will have entries in the relation set itself. The ones that I have not named here are absent from that set. Is that okay? But this is a very clear example of a partially ordered relation. Why is it called partially ordered? Because we cannot establish the ordering between smooth and not smooth and rich. We don't know which one is better. And the beer commercial did not indicate either. Is that okay? That is why it is called partially ordered, because certain items do not relate. We cannot establish the ordering. Okay, looking at this, do you think this ordering or this relation is transitive? Can you identify some of the bridge elements in this particular relation? Yeah, I mean there are at least two bridge elements. Okay, smooth and rich is alada smooth but not rich. Okay, so look for smooth but not rich on the left-hand side this time. Smooth and not rich is over here, and we want to pick the second one. Smooth and not rich is alada, not smooth and not rich. So now the question is smooth and rich alada not smooth and not rich? That would be make it transitive. And the answer is, yep, it does. It's right here. Okay? Smooth and rich is alada, not smooth and not rich. So it is transitive. So once again, it is reflexive. Everything relates to itself. It is antisymmetric. Is it antisymmetric? If you look at it, it doesn't seem obvious, but it is antisymmetric. Okay, so without looking back in the notes, what is the definition of antisymmetric? There's a conjunction. The result of the conjunction has an implication overall. Remember that? So EFR and FRE implies E and F are the same thing. That's antisymmetric. So in this case, you cannot find, you can find it one way but not the other way. So that means the conjunction is always going to be false if F and E are different. If the conjunction is false, what happens to the implication itself? Let me go back and point out what anti-reflexive is. So antisymmetric, not anti-reflexive. Antisymmetric, so we can find this, but we are always missing this one here, right? So that means the conjunction is always false if E and F are not the same. If the conjunction is always false, what happens to the implication? The implication is true. All right. So that relation turns out to be antisymmetric as well. So it meets all three requirements of partially ordered. Is that okay? So the problem with partially ordered is you do not have totally ordered. You cannot rank some of these items. So getting back to here, there is no way for someone to rank and say which one is better. Is smooth and not rich better, or is not smooth and rich better? We don't know. Okay, the relation does not define that. Yep. Question?
Smooth and not rich was E and, or no, there is no smooth.
There's no
Not
yeah.
smooth and rich.
Yep. Yep. And that is why it is not. You cannot show that it is not antisymmetric. Okay. So what does this have anything to do with programming? So think about gaming, okay? Think about, League of Legends, okay? So if they want to somehow, get people to play that game because, we're going to elect, gamer of the week, okay? Using some kind of metrics. How do you find that, gamer of the week? What metrics are you going to use to measure, the gamers, to gauge the gamers? You can use time spent, right? You can use games won. You can use number of minions killed, gold attained, and so on. There are lots and lots of metrics that you can use. So unless you come up with one single number in the end, you might end up with a system that is only partially ordered. You might end up with players where, yeah, I know this player is quote unquote better than that player, and this player is better than that player, but between these two, there's no ordering. So without total ordering, you cannot find the best player, okay, or the player of the week. You might have multiple players that are ranked on top of their so-called hills, but you cannot compare those in the end. So that is why this is of interest in programming, because integers are easy to deal with. Okay, with integers and less than or equal to, it's totally ordered, not a problem. It's only when you use multiple metrics to do the comparison, then you may end up with something that is not totally ordered. Is that okay? How many people, well, since you're supposed to be in 430 in the same semester or prior to this one, you have to understand what is operator overload. So tell me one reason you might want to overload less than or equal to as an operator.
Some type where they might want to use that operation that's defined in that way.
You might have a template class that is used to implement an algorithm, such as sorting. Okay, so you basically go like, okay, as long as this type or class has less than or equal to defined, that this template is going to work. So I can check whether an array is already sorted. I can sort an array if it is not already sorted. Okay, kind of makes sense, right? But if your less than or equal to is not totally ordered, it's only partially ordered, then you have a problem. Does that make any sense? But remember, we are overloading the less than or equal to operator. So when you redefine less than or equal to using multiple metrics, you might accidentally define a relation that is only partially ordered, but not totally ordered. Then the sorting algorithm is not going to work, because the less than or equal to is simply not defined between certain elements. Is that okay? Is that important in your programming career? Yes, it is absolutely important, especially when there's prize money involved in player of the week. Okay? Because then people will ask, how come that person is gamer of the week and this person is not? And then they find out the algorithm has a problem, and guess what's going to happen next? Lawyers are going to get involved. What do lawyers first, what is the first move of any lawyer? Any good lawyer, as in good as in effective lawyer, okay? They find out how much, insurance Riot has, how much is insured. They look at that amount and go like, yeah, we go for that. Because any more is not going to work, but if you just get up to that insured amount, you can probably get the insurance company to pay off. So Riot obviously doesn't want that scenario to happen, which also means it doesn't want its developers to accidentally develop an algorithm that doesn't work because, whoops, we forgot about partially versus totally ordered. So that is why this is kind of important, okay? It's more important these days compared to the good old days of programming. Because in the good old days of programming, we don't have object-oriented programming. Without object-oriented programming, there's no operator overload. Without operator overload, you kind of have to custom define sorting algorithms per type that you define, which means it is not likely that somebody's going to just try to do a plug and play. Oh, I just need to define less than or equal to in the player representation, and we'll just plug that into the sorting algorithm. You cannot do that. You kind of have to re-implement everything from scratch before object-oriented programming. But these days, you can just kind of go like, oh, there's a template class, right? I just plug my type as into the template class. I'm done. So you gotta keep in mind. You need to keep in mind of these things. So what about total ordering, which is the last section of this entire module? Total ordering, as you probably expect, is partial ordering, and one more thing. So we'll take a look at this. The first one is R has to be reflexive. That's one of the requirements of partially ordered. R has to be anti-symmetric. That's also one thing that you have to find in partially ordered. Transitive, okay, same thing. It has to be in partially ordered. It has only one extra requirement. The extra requirement is XR is comparable over X. What is that? We have never defined what is comparable. Comparable is only used here, and that's why I do not define it earlier. Comparable means for all E and F, any way to pick two things out of X, the following has to be true. ERF, which means EF is in R, or FRE, FE as a two tuple is in R. So one of these two, at least one of these two has to be in the relation. Okay. What does that mean? Yep. Any two things are related. Every two things that you can pick out of the set X, they are related. Now, which way are they related? Well, that's kind of up to you, okay? But they have to be related. And this is the extra requirement on top of partially ordered. Is that okay? So we want to double check, okay? So if X is the set of all integers and R is less than or equal to, does that make sense? In other words, if I pick any two integers, okay, E and F, is it true that E is less than or equal to F, or F is less than or equal to E? It has to be at least one of those two, right? Now, if you so happen to pick E and F being the same element, then they're both true at the same time. But even if your E and F are different, at least exactly one has to be true. Yep.
Is there another parenthesis that's supposed to be in there, or is that second parenthesis not?
Yeah, there should be another, or we can remove one parenthesis. Okay, time to fix it. I think there were a few typos in some other notes too. If you guys find it and report it, I can fix all of those. Yep, here's the double paren here. There we go. And scroll all the way back down. And now we have single parenthesis. But this is also the other way to represent, in the previous, discussions, I say, EF as a two tuple is in R. This is just the other way to say the same thing. It's more convenient this way, but the set notation is no longer as clear. All right, so are we good so far with relations? So we got a few things. We got the pine needles, okay? The pine needles would refer to exactly how each property is defined. We got the pine tree. The pine tree basically is, why do we need to know about these relations? What exactly is a relation in regular programming? Well, all of those comparison operators are relations, okay? And then the forest is basically asking, why is this important in my programming or software development career? Well, it's because you have to understand whether something is partially ordered, which you can easily define, or whether it is fully ordered or totally ordered. If something is not totally ordered, it cannot be sorted. But there are certain things that you can do with partially ordered relations, but totally ordered is typically what we need when we work on algorithms. So are there any questions? No questions? Yep, go ahead. If it's only partially ordered and it does not meet this requirement, then it cannot be sorted in general. Now, if you so happen to only have the elements that within that subset is they all have relations defined, then within that subset of elements of X, you can still sort, but in general, you cannot. All right. So how important is the concept of sorting and ordering in computer science? It's very important, okay? So that part is also very it's key, because if I keep talking about something that is not important in computer science, then we have just wasted like 1.5 classes. But because ordering is a big thing, it's very important. That's why this topic is also very important. So are we good so far? All right. So this is relations, and then unless there are questions, if there are no questions, I'm going to move on. And let's see, the homework assignment for functions is due on Wednesday. So that means I'm going to release the relation homework on Wednesday. So this way you don't have two active homework at the same time. So now we're going to move on to propositional logic, which is a fairly big topic. It's a bigger topic compared to functions or relations because there are several perspectives to propositional logic. Okay. So before we go any further, it might be helpful to kind of explain the background of propositional logic and why it is important today in computer science. So one thing you can do easily is to just do a Google search. Okay, so you search for propositional logic, and Wikipedia has a definition, and many other. It's also known as propositional calculus, which has nothing to do with the actual calculus that you take here. Okay. So if you look at this one, it's a branch of logic. It is also called propositional logic, statement logic, da 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 da. And then you look at the history of this. So you look at the history and you go like, okay, does it relate to computer science? Does it start to exist after computer science? Or does it exist like way before computer science? So let's see, we click on history. And we are looking at 3rd century BC. This is nothing new at all.
So computer science is not here.
Hmm?
Computer science is not here either.
Computer science is relatively new, okay, because Alan Turing developed most of the computational theories in the 40s, in the 50s. So it's relatively new, but the Boolean logic that it's based on is not new at all. Okay. So, but in this case, it is done by several people, in 300 BC. So it's nothing new at all. It's basically the mechanical aspect of arguments. Okay, so you read some statements. Okay, fine. Give you an example. You go to McDonald's. Okay, or some fast food chain. They say, if you meet these requirements, you get a free toy. Okay. Okay, well, that's what it says. So, and then you walk in, and then you think you should be qualified for a toy, and you didn't get a toy that day. What are you going to do? Well, you're going to go back to the fast food place, and you argue for it, right? So whatever argument you use to get your toy back, okay, at the fast food place, it's based on logic. So propositional logic is really just a system to tell you, how you can derive truth. Okay, if this is true and this is true, that has to be true, and so on and so forth. Okay. And now would be a good time to show you kind of like a graphical representation of any type of logical proof. So we are not talking about really just proofs that we do in this class or proofs that you do in calculus. We're talking about general speaking. What do you do? What are you actually doing when you are proving a particular theorem, a statement to be true? And we're going to use the tablet. And I know some of you are thinking, oh, no, not the tablet because it has so horrible lag. Well, guess what? I did this over the weekend. I researched, and I found a really, really good alternative to the software that I have been using. So the lag time is totally reduced. It's not gone completely, but it's definitely much more usable than before. So let me go back to 440. And this is 418. All right, so the test is, I'm just going to spell out the letters that I'm writing here. So A, B, C, D, E. Not too bad, okay? About maybe a quarter to a half second of lag. Much better than 3 or 4 seconds, right? Okay. So I'm gonna take this away. So remember what I was about to do? I want to show you graphically what it really means to be proving a theorem, okay, in any class. Okay. So I'm going to put a box here. So this entire box represents everything that you can say, okay? True or not, this represents everything that you can say. So you can look at this box as containing every syntactically correct logical statements. Okay, every single Boolean expression you can ever write that is syntactically correct is in this box. Okay, so every single pixel here is representing a single expression that is Boolean. It can be true, it can be false, but syntactically it is okay, it's correct. Is that okay? All right. So with any type of system, you are given a certain set of expressions which can be constants that are known to be true. Do not ask me why it is true because you are told it is true. Okay? So we call those axioms or constants. Just true by itself is basically always true. So I'm going to use circles in red to represent things that are known to be true. And just to illustrate the whole idea of what is a proof, I'm going to put some blue dots here. So all of these blue dots are expressions that we are interested in, and so on, like so, okay? So one day, after taking a class, usually the first few classes, they only talk about the axioms. So can someone tell me an axiom in algebra? Certain properties we know about addition and multiplication. Okay, a plus b is b plus a. That's called the commutative law of algebra. Go ahead. Associative law, which means in parentheses a plus b plus c outside of the parentheses, is the same thing as a plus open paren b plus c close paren. Okay, so we know a bunch of rules like that, and those are all encoded in red. Okay, so one of these spots here, I'm gonna pick out this guy all the way here, is the theorem that you want to prove. Okay, some blah 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 expression equals to the some blah 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 expression. Okay, and you're asked to prove the equality. Okay, it sounds like a fairly common type of exercise in algebra. Is that okay? All right. So then what do? You basically are proving by propagating the red circles. In other words, there are mechanical rules that says, oh, if this thing is true and this thing is true, guys, what? That automatically makes this true as well. Okay? If this is true, it makes this thing true as well. So I need to use arrows to indicate the direction because they're all implications. Okay? If both of these are true, it implies this is true. If this is true, it implies this is true. So we'll do a few more of these examples. So if this is true and that is true, it implies this one is true. So you have ways to propagate the labeling of the red stuff. Okay? So eventually, okay, so I'm just using this as an example. Okay, these two go here as well, and then these two go here. So everything, is stuff are starting to get labeled in red. Okay, and then eventually you find a way to connect to the last one here, which is the theorem that you're trying to prove. That is what a proof is about. In an infinite, usually it is an infinite space of syntactically correct expressions. You are trying to make connections between things that are known to be true, that are given to you to be true. You're trying to make that connection, make connections all the way to the one expression, the one Boolean expression that you want to be true in the end. If all of these things connect in the end, then you have just proven the theorem to be true. Okay? Is that okay? Yep.
So in propositional logic,
Uh-huh.
other statements that you can make that are not provable using the axioms, right?
Okay, you have to say a little bit louder.
Other statements that you can make that are
So if it's not provable, which means there's no way to propagate the red circle to those particular statements, then they are not theorems. They are not conclusive from what you know to be true to begin with. Now, doesn't mean that they're always false. It simply means it does not follow. Okay? I'll give you an example. So let's see if I can give you an example like this. Okay? Okay, so some people in CISP 440 will get A's. Okay? Now, remember, this is just an example, so do not hold me accountable for that. Okay? And let's say, in general, so once again, do not hold me accountable for this. I'm just using an example. People who get A's in classes become geeks. Okay? Now, the quantifiers are missing. So what do you think are the implied quantifiers? Let's start with the first one. Some people in CISP 440 will get A's. What is the implied quantifier here? Is it the universal quantifier, which is for all, which also is known as every in English, or is it the existential quantifier, which in mathematics is known as there exists, but in English is known as some? Is existential, which means at least one person in CISP 440 will get an A. Okay? What about the second one? People who get A's in classes become geeks. Is it universal or is it existential? It is usually implied to be universal. Okay? But if you want it to be, if that is the intent, then you have to say every person. Okay, that makes it very clear. If you want to make it existential, then you say some people. Okay, so you kind of have to make it non-ambiguous, because this particular statement is ambiguous because it's not clear which way we want it to be. Okay, so we'll just say that some. Okay, so to make it extra clear. So some people who get A's in classes become geeks. Is that okay? So given these two are true, okay, so you're told that these two statements are true, okay, what can you infer? Some people who get the grade of A in CISP 440 will become geeks. Can you say that? If this is existential, you cannot make that link. You cannot say there exists at least one person who got an A in CISP 440 will become a geek. That is not possible. That you cannot draw that conclusion. Even though it seems to make sense, you cannot draw that conclusion. Because some people who get A's in classes, remember, this is classes. This includes CISP 430, 400, 360, and so on. And all we need is one person from one of those classes where that person is an A student and eventually becomes a geek for this statement to be true. That person may not be coming from CISP 440. So that's kind of the logic that we are talking about that you have to be careful about. Okay, so but in order for for this one to make sense, we'll just change it to everyone. Okay, everyone who gets an A in classes, or at least one class, become geeks. Okay, so to be extra clear, everyone who gets an A in at least one class become geeks. So that's a really, really specific universal statement. So we'll just say that that's true. So what can you infer now, given that these two statements are kind of modified the way they are? Someone who gets an A in cisp440 will become a geek. Okay? But does that mean there's at least one person in the entire world who is a geek? Not necessarily so. What if cisp440 has never been offered? Then even though these two statements are true, we may not have a single person who's a geek in the entire universe. Is that okay? So now the theorem that we want to prove is, okay, someone who got an A in cisp440 is a geek. So if this is the theorem, can we prove the theorem based on the statements? Yep.
So the second statement, everyone who gets an A in at least one class becomes geeks.
Become a geek, becomes a geek.
Prove that everyone who gets, or someone who gets an A in CSP, what if they got an A in a different class?
Sorry?
What if they got an A in a different class and not in CSP 440? That doesn't imply that everyone in CSP 440 gets an A and become a geek. Or is that not? What if someone has two different classes? And they get
Oh, you're right.
Is that allowed?
Yeah, so that means it still doesn't connect. But that's great, because this simply means the theorem cannot be proven. The statement is syntactically correct, quote unquote syntactically correct. It has a meaning, but these two combined, the given facts, does not guarantee the statement that I want to prove. That's a perfect example of a statement that is not a theorem. Thank you. So it works either way. Okay, is everybody understanding this part? You can kind of look at, but why is proving a difficult thing to do in your classes? In general, and why do you think it is particularly hard when you are doing research? In other words, you are not reading a textbook where, these are well-known theorems, and I just want you to go through the exercise to prove it. As opposed to, I think that is true, but how do I prove that? Why do you think that's a difficult thing to do? Yep. It's not necessarily provable. Thank you. Very good. So the problem is, if you look at the universe of all the theorems, all the possible statements, usually it is infinitely large. So think of a haystack that is infinitely large. So what is usually associated with a haystack? The needle they want to find, right? So the problem is, okay, I'm asking you to find the needle inside this haystack. The haystack itself is infinitely large. Okay? That's your usual exercise in your math class. Is, yeah, we know that needle is in the haystack, you just have to find it. But the haystack is infinitely large, so if you go in the wrong direction, you can keep deriving, not productively, and not be able to prove in the end. Okay, but what if I say, I don't know whether the needle is in the haystack or not, but go ahead and try to find it. And the haystack is infinitely large. Don't you think that problem is a little bit difficult? Yeah? So what we'll do today, or not today, but in the next few classes, what we'll do is we'll find a way to make that problem easier. In other words, if you know the haystack is only so big, then even in the off chance that the needle is not in the haystack, you will still be able to tell me, I have searched through the entire haystack, the needle is not in it. Okay, so we'll try to fix that problem by making the space finite. Okay, so but this is the kind of problem that we are dealing with. It's not necessarily a mathematical proof, it is just logic. Okay, so how do we apply logic to prove something? So are we good so far? Okay. So let's go back to the notes here. All right, so when we talk about propositional logic, we usually represent it as a for tuple. Okay? So there are 4 things to a propositional logic system. It's kind of like defining a programming language, okay? So there are multiple components. The first one is alpha. This is the uppercase alpha symbol. Looks like an A. It's just a set of symbols. So if you want to equate this to programming, this is really just defining what characters are legal to use in a programming language. Okay, in C you can use uppercase A to Z, lowercase a to Z, the underscore as variable name, right? So that's just the rule, like that. So A is consisting of the alphabet, okay, of whatever system you want to deal with. And I can give you an example here too. Constants would be 0, 1. 0 is false, 1 is true, okay? Then we have variables, P, Q, R, S, T. Those are typically what we use as variables. And then we have something other than variables. You can kind of call those super variables. And those are the Greek letters, like lambda, not lambda. We usually use theta, psi, and so a rho. Okay, so those are the typical characters for what we currently would kind of call them super variables. And then we have syntactic rules to basically say, how do we combine the symbols? Those are called the operators. And that's what the set omega is about. So the set of omega is defining a bunch of operators. And each operator may require a certain number of operands. Okay? So what operators are we talking about in the typical logic system? Disjunction. Okay? Disjunction needs 2 things. Conjunction needs 2 things. Negation needs 1 thing. Implication needs 2 things. If and only if needs 2 things. Okay? So that's what omega is about. It's a bunch of operators. So between alpha and omega, you can now generate expressions. Okay, so I'll give you an example. So you can say, okay, let's just say that alpha, which is the set of all the usable characters, consists of false, true, and then just P, Q, R. Okay, so I'm limiting myself to a fairly small alphabet. And then I define omega to the usual operators. So we have negation, which only needs 1 operand. We have conjunction, which needs 2 operands. Disjunction, conjunction needs 2. Disjunction needs 2. Implication needs 2. And then if and only if also needs 2. So we have that. Okay. And it's also implied that these will be using the infix notation and parentheses are allowed. Okay. So that's kind of like the implied allowance. So from here, I can now generate syntactically correct statements. Okay, so I can say false and true. That's syntactically correct because the operator and needs 2 things, and it is applied with 2 things. So I don't know what the value is, but I know this is syntactically correct. Not a problem. We have P or true, and then the whole thing and false. Okay. Now, of course, based on semantics, you guys would go like, why do you waste your time with this expression? Okay. We are not concerned about semantics. We are not concerned about whether it's true or not. I'm only concerned about syntactically, is it correct? It's correct. The OR has 2 things applied to it, which is exactly what it needs. The result of the OR becomes part of what the AND needs. The AND has 2 things applied to it. It's syntactically correct. Okay? I can show you something that is not syntactically correct. Okay? That is not syntactically correct because negation only needs 1 thing, but now it's used as an operator that has left-hand side and right-hand side. So this is not okay. It's not syntactically correct. Is that okay? So I'm just going to put a cross here to indicate that this is not syntactically correct. But you can also see how with only 5 symbols defined in alpha and having an omega that is just reasonably large for the logic system, I can now crank out an infinite number of expressions. The simplest one is just saying 0, 0 or 0, that whole thing or another 0, that whole thing or another 0, that whole thing or another 0. I can keep stacking zeros, or zeros, and those are all syntactically correct. Is it meaningful? No. But are they syntactically correct? Yes. Are they inside that big huge box of syntactically correct expressions? Yes. Okay? All right. So that takes care of alpha and omega. And let's see what else is here. Here's zeta. Before we get to zeta, let's talk about iota first. So iota is a set of well-formed formulae, which is a fancy name of expressions that are syntactically correct. Okay? So next time you see WFF, which is not WTF, and then at some point I know some smart student is going to say WTF, WFF. Well-formed formulae is no more than a fancy word or fancy phrase of syntactically correct expressions. Okay? So iota is basically a set, usually a finite set, where I give you all the well-formed formulae or all the syntactically correct expressions that are known to be true. 1 is known to be true. Not 0 is known to be true. P implies Q may be known to be true. It depends on what kind of logic system I'm trying to model. Okay? P or Q may be known to be true. Okay? So it's just a whole bunch of expressions that are known to be true in order to model a particular reality. Is that okay? So given alpha, we know what letters we can use, what constants we can use. Given omega, we know how to combine the values. We know how to combine constants and variables to make more complex values. Given iota, we are now given what is known to be true to begin with. Okay? But the most important part of a propositional logic system is zeta. Zeta is basically a set of transformation rules, which we call each one a production, where you can look at two well-formed formulae and go like, oh, if both of these things are known to be true, that is known to be true too. So you can actually derive new, quote-unquote, new well-formed formulae that are also going to be true. But in reality, the expressions are already there inside that universe. All we are doing is label. Okay, these things are pre-labeled to be true. Okay, what else can we label? Oh, if this is true and this is true, we can label that one to be true too. So we are basically propagating the labeling until we get to the one expression that we want to prove. Is that okay? So it's basically the mechanics of arguments. Okay, what is known to be true? Okay, do we all agree that all of these things are true? Yes. So can I now argue that that is also true? No, that doesn't seem right. This seems right. Okay, see if I can logically connect the dots and prove that the theorem is also true. That is basically what the propositional logic system is supposed to do. Are we doing okay so far? So why do you think somebody was interested in this in 300 BC? They don't have any computers. Why is this of interest? Go ahead. Philosophy? Because people like to argue, right? And this is basically what is the mechanics of arguing, okay? Okay. How does that have anything to do with computer science today? Okay, so let's put this up on the shelf for a little bit, okay? And then what we want to do now is to kind of fast forward from 300 BC to today. When was the last time that you patched Windows? A few weeks ago? Yesterday? A few hours ago? Huh? Whenever it wants to. Very good. Okay, so that's a very good answer. But the frequency of patches is very frequent now, okay? When was the last time that your Android or iOS phone decides to, oh, I need to update all of these apps? It's kind of like a continuous basis, right? And why do we have all those patches? Some of those are new features, but most of them are not because of new features. Why do we patch software? Yep. Well, the hardware changes, but you're not getting a new phone. Between the times that you get from using one phone and your new phone, how many times have you patched your operating system, the individual apps, and so on? Yeah, too many times to count. Yep. Security is one. Okay, so security is a big thing because it ties in with money. Okay. Why do we have all these security patches? Huh? Because they can be broken by people, by hackers, right? So, okay, so regardless of the motive of someone, okay, go ahead, sorry.
It's because people find loopholes in the logic.
Because, oh, very good, because people find loophole in the logic that we call vulnerabilities, okay? So tell me one form of, vulnerability that has been causing problems. Just name one. Hmm? Buffer overflow is a general mechanism, where people can gain unauthorized access to programs. Okay, so buffer overflow is one, but that's a software thing, right? So people might think, oh, well, these are all software issues, and it's the software people who are at fault all the time. Name one vulnerability that has to do with hardware. There are two, but give me one. Spectre. Okay. So what is the problem with Spectre? Why is there a problem to begin with?
I don't think it was smart enough to explain that.
It has to do with a caching mechanism. Okay, it's basically it's a race condition. Okay, in hardware, it's basically saying, okay, who gets to get to the other point first, and whoever gets to the other point first, is get to the information. So there are all of these vulnerabilities. Why do you think they happen? I mean, in some cases, you can kind of say that, well, maybe a spy was planted into a software company and they intentionally put a backdoor into the software. Yeah, that kind of happens, but that's not the majority. Yep.
It's the way people may set about, it's the logic in the chip.
The chip and also the software. Okay, so the logic of the chip and the logic of the program contains quote unquote faults. Okay, so what is a fault of a particular? Let's not even talk about programming languages. Let's talk about just pseudocode. Okay, and a general approach of solving a problem. What is a fault? What does it look like? And how do you define that? So if I ask you, okay, we talked about this a little bit before. If I ask you, how do I describe the proper output of a sorting algorithm? Remember that one? Okay. So there's a certain description, okay, that we can use, the universal quantifier and a whole bunch of other stuff functions, okay, bijective function in that case, to describe the proper outcome of a sorting algorithm. So if we can describe the proper outcome of an algorithm, what do you think a fault is going to look like? The outcome of an algorithm does not equal to the mathematical description of the proper outcome of the algorithm. They do not equal. Okay? So if you remember, the proper outcome of the sorting algorithm looks like a really kind of long, complex, logical expression, right? And then you start with the given condition, how big the array was, what you know about the array, blah, 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 okay? How do you prove that? Can you prove that? Can you prove that your algorithm is correct or incorrect? I'll show you an example, okay? We'll show a simpler example of, how to analyze an algorithm. So let's say we only have two variables, x and y, to begin with. And I want z to be the maximum of these two. Okay? So I want z, the output of the algorithm, to be the maximum of x and y. Okay. So instead of using this notation of z equals to max of xy, can someone tell me how to define the maximum of two values? Sorry? Okay, so we'll try a few approaches. Okay, so the one way is to say, okay, back. Okay, z is greater than or equal to x, and z is greater than or equal to y. Would that properly define that z is the maximum of x and y? No, does not. Because you can be given x being 0, given y is 1. I just have to make z the largest possible integer that can be defined. Then that z is automatically greater than or equal to both x and y, but yet it is not the maximum of x and y. What am I missing? The maximum has to equal to one of those two. Yep, so we need another condition. Okay, we need to say and z has to equal to x or z has to equal to y. Because without this, I can just make z the largest possible integer and call it a day. But that would not be the proper way to find the maximum. Is that making any sense? Okay, so now that we can define the proper property of the condition, or this is called the post condition. It's the condition after the algorithm executes. So now that we can define the proper post condition of the algorithm to find the maximum value, now I give you the code. Okay, so I give you the code, which is relatively simple. If x is less than y, z equals y, else z equals x, close paren. Okay. I know my penmanship is really bad, but the idea is just that, okay? Seems right, right? So what do? You run a few examples, you run a few numbers through it, right? You compile the program, and then you say, okay, what if x is 20 and y is 65? Okay, seems to work. What if x is 0 and y is negative 10? Seems to work. Well, what makes you think the next test case is going to work? Now, in this case, there is a finite number of test cases. So if x is a 64-bit number, y is a 64-bit number, you're looking at 2 to the power of 128 possible test cases, which is technically a finite number, but it's pretty big. Okay, and we are only talking about two integers now. What about the SS? Let's see. It is the SSL library for encryption. Do you think it only has two 16-bit, 64-bit parameters to give you 2 to the power of 128 finite possible test cases? No, because you're dealing with packets of data now. So how do we know the algorithm is always going to give us the correct result? You can spot check it, but the problem with spot checking is like you're throwing darts. So think of the scenario where you have a board behind a piece of paper that's opaque. Okay, so on the board itself, okay, you can have little red dots, here and there. Okay, those are representing the cases where the algorithm is not going to work correctly. The rest is going to work correctly. Okay, so now you pull a screen over, the board itself that's opaque. Spot checking is the same thing as throwing a dart, okay? And then go like, is that a little red something behind it? Nope, okay, throw again. Is there a little red dot behind it? No. So you throw 100 times, okay? And probabilistically speaking, depending on the density of the red dots, you may not hit a single red dot in 100, 1,000, or 10,000 throws of darts. Does that mean your algorithm is okay now? No, it simply means that you haven't hit one of the red dots. So testing software by test cases, especially random test cases, is not going to catch problems. Okay, It will give you a general idea that, yeah, the program seems to work most of the time. But does it work all of the time? We don't know. Maybe. Okay? So what is the problem of, why do you think I mentioned SSL, Secure Socket Layer, in particular in this case? It has to do with a vulnerability that is fairly well known. What is the name of that thing? It's called hard bleed. And there's a website for it. And it looks like that. So with a hard bleed bug, okay, which is completely a software vulnerability, which exists in all the SSL engine in OpenSSL library at the time, people can poke a server and be able to retrieve quote-unquote random chunks of the memory of the SSL engine and retrieve that. So what that sometimes may contain would be passwords, it will be the encryption key and other really, really sensitive data that the server has maintained in its memory. Needless to say, this was a big deal, okay? But the problem is, we tested the program with proper packets and requests and stuff like that, and it worked fine. It's the ones that is not well formatted that you have to worry about. How many ways can you malform a packet compared to how many ways you can form a packet correctly? There are a lot more ways to make a wrong packet than there are ways to make a right packet, right? And guess what kind of frame the program is going to be in when the program is trying to program in the processing software to deal with a request packet. What it is supposed to look like, right? So making the assumption that the input packet is what it is supposed to look like, the programmer may forget to do certain things to check what if the packet is not what it is supposed to look like. Okay? Classic example, string compare without the n. What is the problem? String copy, sorry. String copy without the n. String copy says, I'm going to copy everything until I find the null character. Okay? If the packet standard, if the standard says this packet can only be 100 bytes long, okay? If the frame of mind of the programmer is to say, yeah, okay, I'll write my program to parse what is supposed to be expected, the buffer is only 100 characters long. What if I want to copy that portion of a buffer to another buffer for processing? String copy, because I assume everything is playing by the rules, right? What if someone says, I'm going to try to break your program. I will make this section 200 bytes long. The program is going to use string copy. It will keep copying until it sees the null character, which means it's going to copy 100 bytes beyond the end of the buffer. It will start to overwrite certain other memory locations, depending on whether it's heap-based or stack-based, but it will overwrite something. Now, if it's on the stack, and you have taken CISP 310 from me, then you go like, oh, it can overwrite all kinds of fun stuff, like the return address of a function. It can overwrite, the values of some of the local variables of the callers, okay? So what do you think, if you have fine control over what you're overwriting, and you know exactly how you're supposed to overwrite it to gain control over the software, what's going to happen? It's going to be hacked, okay? So the bottom line is, we have a mathematical description of what the program is supposed to do. We have a program. How do we prove that the program will only do what it is supposed to do and nothing else? Question?
Don't we have to provide it some kind of set and make sure that it follows all those rules?
You have to make sure that it does process correctly when it is given the proper packet, but you also have to make sure that if you feed it a packet that it is not supposed to process, it will come to one of the exceptions or erroneous state, or somehow catches that and go like, I'm not going to process this. So the last thing, okay, just one more word, automated theorem proving. This is why we are interested in propositional logic in a computer science class. As opposed to a philosophy class or some other classes, we want to make computers to be able to prove theorems automatically. That is the reason why we are on this topic. So I know we are running out of time. This is the last thing I want to mention. I'll see you guys on Wednesday.